Many transitions observed in DSC are complex because they involve multiple processes. Examples include the enthalpic relaxation that occurs at the glass transition and the crystallization of amorphous or metastable crystalline structures prior to or during melting. Enthalpic relaxation is an endothermic process that can vary in magnitude depending on how long the amorphous material has been aged. For instance, under some circumstances, it can make the glass transition appear to be a melting transition. Simultaneous crystallization and melting make it nearly impossible to determine the real crystallinity of a sample prior to the DSC experiment. These problems are compounded further when analyzing blends of materials. Conventional DSC does not allow these complex transitions to be properly analyzed since it measures only the sum of all thermal events. Hence, when multiple transitions occur in the same temperature range, it can be confusing and misinterpreted. Modulated DSC, or MDSC, is a technique which provides unique information not otherwise available, which overcomes most of the limitations of conventional DSC. In MDSC, a different heating profile is applied to the sample and reference pan. Specifically, a sinusoidal modulation or oscillation is overlaid on the conventional linear heating or cooling ramp to yield a profile in which the average sample temperature continuously changes with time, but not in a linear fashion. The net effect of imposing this more complex heating profile on the sample is the same as if two experiments were running simultaneously on the material. One experiment at the traditional linear heating rate and one at the sinusoidal heating rate. The actual rates for these two simultaneous experiments are dependent on three operator selectable variables: the underlying heating rate, the period of modulation, and the temperature amplitude of modulation. In the case of cyclic DSC, the material is cycled between low and high temperatures to note the changes in the material with time and temperature. Some events in DSC may be reversible and some irreversible. In cases where the events are irreversible, cyclic DSC comes in handy to isolate the phase of interest. Consider an amorphous phase at room temperature that has a glass transition but an accessible crystalline phase with a high melting point. In this scenario, cyclic DSC can show the temperature at which the rubbery amorphous material will recrystallize, and once cooled, the recrystallized sample can be isolated and further investigated.